universe is screaming with secrets. Are you listening? Join renowned astronomer and History Channel analyst Mark D'Antonio for a journey across the light years.
We're looking at stars that died before we were born and planets that might just be looking back.
From the mysteries of deep space, live feeds from the Sky Tour live stream telescopes, we're bringing the heavens to you. It's the Sky Tour Radio with Mark D'Antonio. Look up, look up, look up, look up. The show is about to begin.
Hey everybody, this is Mark D'Antonio and that's Tara.
Hi, hello, Mark. Hi everyone.
And we are live on this July 19th, 2026. Is this thing on? And we're actually gonna have some fun tonight. We're gonna go through a bunch of Hubble and JWST discoveries and talk about some real stuff that makes a big difference. We're also going to do a post-mortem analysis on 3i Atlas, because we're wondering what that was all this time, and we kind of think we know.
Good.
We'll discuss that.
It was a spaceship.
Yeah, it was definitely a spaceship, but it was the planet killer from Star Trek, the first series, a big conical, one of those old cracker things, the bugles.
I forgot about that. Yes. You're right.
Somebody actually produced a picture of that and said, "This is 3i Atlas." And you know what? There's people out there that said, "Yeah, I'm sure that's it." Oh no.
And they extrapolated that from a pixel or two.
They actually, yeah, exactly. It was at that time. It was only a few pixels in size on an image frame, and we took a bunch of images of it. And I'll show you some today. Or a one anyway.
Beautiful. Yeah.
I tried to bring up our moving and animation of it, but the animation wouldn't load. I don't know why. But hey, you know what? That's what you get, right? I don't get it, But it's so good to see you. I haven't seen you. What have you been up to?
I know. Oh, just this and that, and surviving this Arizona heat and humidity, because we normally don't have humidity.
Well, you're in the monsoon season now.
Yes, we are.
And I've noticed that Arizona is full of clouds.
It's full of rain clouds.
Yes, and how would I know all that?
Gee, you might have a telescope or two, huh?
Or two.
Soon
to have three. Yeah.
Awesome.
Yeah. We're going to talk about that.
4. Yes.
Yes, that's right. And there will be a fourth one out here in the east, because I'm going to be adding a solar telescope to this entire menagerie of telescopes very soon.
That'll be so fun.
Yeah, and that's something that will be on this end. It'll still be an automated observatory. It's going to open and close when I tell it to, and I'm not going to have to go out and do it, like I did with the first one. I don't know if you remember. The telescope that I had was, you can kind of almost see it. I'll move this. Okay, there it is back there.
I see it.
You can just barely see it right there. That was the very first Sky Tour live stream telescope, and it was out here on the front lawn, about 75 feet out in front, and beautiful view of the southeast and the west. But it ended up being impractical after a while, because it was in a dome, a real dome, which looked like a giant minion.
That's cool, though. Yeah,
it was. Yeah,
you could tell there was a telescope.
Yeah, our producer Bill was here with people and checked out the dome. He remembered it, and it was a lot of fun. And the only trouble was winter wasn't fun
for you.
No, it was like there was days that I was in the dome at 10 degrees.
That's what I mean.
And you can't warm the inside of the dome, because it's got to be the same temperature as the outside air. So what it means is you got to open the shutter and let that cold Arctic blast in and equalize all the temperatures of everything, including the telescope and you. Not fun.
I do me first and then the telescope.
Yeah, I had hand warmers in all my gloves. I had them in on my thighs. I had them in my shoes. And at the end of the night, it was like 20 minutes just taking all the hand warmers out because they're all the sticky ones, stuck to things. It's like had them on my chest.
So that's operating in extreme cold. How cold did it get when you were using the telescope?
The coldest I've run the telescope was around 3 below zero.
Oh my goodness!
It works fine, but I don't.
Especially in the dome.
I'm going to go use the camera. I'm going to touch the camera. Frozen.
Oh my God! Yeah, yeah, that's scary.
Yeah, when I was working in a big observatory, the coldest temperature I worked in there was 10 below, and I had to work all night from midnight to dawn in the cold without getting into warmth. Because if you got into warmth and then came into the dome, I mean, it was a big dome. It was a 20-inch refractor, so the building was easily 50 feet in diameter with maybe 40 feet in diameter with a big dome, but you couldn't bring that warmth in because it would somehow migrate to the upper part and go out the slot in the dome and would cause the images to do this, and you couldn't have that kind of.
Even in that big of a place. That's crazy.
That big of a place. Yeah.
It's amazing.
And then after I took the pictures, we were taking them on glass plates with a film emulsion called 103AO, which, by the way, is notorious for making artifacts on your final images, as it turns out.
Oh, so those weren't planets after all.
They weren't planets. They weren't stars either. And so we had to eliminate the bad images, the bad parts of the image before we sent these plates down to Yale to have the measuring machine start measuring the images and calculate our plate scale, figure out everything, and then figure out the actual movement of the stars. We're doing parallax. So like if you hold your hand out at arm's length and you blink your eyes, you see how the finger shifts against the farther background.
Yeah.
If the finger, I know it looks silly. Hey, look at me. Okay.
Oh, I was doing both hands. That looks silly.
It does, yeah. Yes, exactly. but if the finger's a star that's nearby and the distant wall are the farther stars and the distance between your eyes is the Earth's orbit, you can see how you can get the same effect with nearby stars. And so we can use that shift distance, what's called a parallax angle, to figure out how far away the star is.
That's so cool.
We had hundreds and hundreds and hundreds of stars that we looked at in the course of the work. And that's where I cut my teeth on big telescopes, is on the parallax program. Then I decided I had to do it myself. So not parallax, but just astronomical research stuff. I did a photometric project where I studied the brightness of stars, and I was able to discover that how we have the OBAF GKM stars, and you remember this diagram that we had. Okay, across the bottom you see the OBAF GKM. The O's are the hottest and the bluest, and the M stars are the coolest and the reddest. If they're on that line you see in the middle that snakes through. Okay, well those set of stars, you see the B stars there. There's like the O and then the B right next to it.
Right.
Okay. I studied B-type stars, and I was able to discover that there were some B-type stars that were literally speeding out of our galaxy at high speed. So something grabbed them and was gravitationally whipping them out of our galaxy. And to find B-star candidates that were speeding that fast defied all known knowledge at the time. So we knew they could exist, but that study showed they did. So I was really happy to see that.
So slingshot around a star, perhaps, or something.
If you have
or an explosion. I mean, how would that move?
But probably not an explosion, but probably what you said. I mean, if you have a cluster of stars here, and another star comes in, that combined gravity of these clusters of stars can whip that thing around and send it out, and it might have the escape velocity to leave the gravitational pull of those stars and the others around it. And so those are called runaway B stars. Now, heaven forbid you had like a runaway G star with planets, because no one around the G star would ever know. It wouldn't pull the planets away from anything.
It'd be like we are now. We don't even tell we're moving, right?
That's exactly right. We wouldn't know it. We wouldn't see it. We would just notice over over millions of years that the galaxy's getting smaller and smaller and smaller and smaller as we're going further and farther and further away. Yeah,
That's neat.
reminds me of that science fiction show, Space 1999, where the
Oh,
moon was
yes.
blasted out of the Earth's orbit. Remember?
Oh, I forgot
Yeah,
about that. That was a good one.
totally
Silly.
silly, totally nonsensical, but
Yes.
fun. Hey, you know what? It
What?
wasn't good science fiction, but it was all we had.
Yeah, cool, because it was all we had. And
That's right. That's right.
times
So
change.
things are well. Now you had mentioned that you have acquired yet more animals. I'd like to hear
Yes,
about those
well,
real quick.
I'm fostering 2 little baby kitties. They're like little baby kittens. There's a litter of 8 living outside in this heat, and
Oh my gosh!
these I know. I already have others in the house, but I picked up 2 that weren't moving very much at all, and they're
Oh
starting to
wow!
eat. I've had them for 2 days, and one's running around, the other one's still a little lethargic, but I'm hoping they'll pull through. And we're trying to find homes for all of them. So,
Okay.
and they're so cute. So, yes, been busy with kitties and rainbows.
And parrots.
And parrots. That's right. I got those wonderful parrots. They're awesome.
Yeah, yeah. Paylone's doing well.
Halon's doing better. He's letting me pet his head and still bites when he wants. And
What a way to say. Yes, it's like saying, and the leopard still attacks me when he wants.
yes, I just let him.
My bear's always raking my face with his claws. Whatever, you know.
It's just a love tap. It's
a love rip.
oh, yes. Yeah, you just kind of
That's-
meet them where they are, but it's a joy to have all these animals. I'm really grateful.
Yeah,
So,
yeah. No,
good for
that's
my
cool.
soul.
I'm really excited
Thanks
for
for
you
asking.
to do that. Yeah.
Yeah.
Around here, the excitement is, here on this beautiful fertile earth of ours, um, I can no longer go outside without a flashlight at night because we seem to be having an epidemic of bears.
Oh,
So
no.
I have lots of black bears now. It's like they can't get at my garbage anymore because I've got this fortress of a garbage bin made by a neighbor out of it's 18th century wood. I mean, it's literally 1700s.
Oh,
That's where it comes
my.
from, and
Cool.
it's 1 inch thick. And I think out of respect, the bear isn't trying to tear it apart.
It's an antique. Right. Yeah.
I mean, there's claw marks on it, but
Wow.
And then I saw a family of 5 raccoons trying to get into it last night on my camera. They're so
Aw.
darn cute.
They are. Until they bite.
I'd raise a raccoon. I'd enjoy it. You got to get them when they're little babies, though,
Yeah.
for them to be more domesticated.
Yeah, I'd raise raccoons and skunks. So,
Skunks are fun the way they bounce. They
oh, they do. They tap their feet, and then they poke their tail like they're spraying you. I've had a couple skunks. That's how I know. So,
I only had the one in my shop that visited me.
Skunky.
It's skunky. That's right. Wild skunk. In fact, somebody was so enamored by that story that they actually got me this little plushy skunk, which I think is really cool.
Cute.
And I use it like it's
Very
alive.
sweet.
I move it around,
Aw.
Yeah, it's cool. Yeah, but anyway, so here, on Sky Tour Radio tonight, we want to talk about a whole bunch of really cool things, and one of those things that we want to talk about is that thing that came through the solar system, this past year that was really, really amazing, and that's 3i Atlas. But first, I do want to bring up a concept that is being revisited. We've talked about this before, but I'm going to do it again because it actually has some relevance. It has to do with stars that eat other stars.
Okay, that's kind of cool.
Yeah, usually we talk about this around Halloween, cannibal stars, zombie stars, but these are cannibal stars. Now, in that diagram I showed you earlier, that amazing chart here.
The O be a fine guy and kiss me.
That's the one. Yeah. Okay. And looking at this diagram, okay, you'll notice that just below that snaky line, you see the white dwarfs there.
Yes.
Those stars are no longer doing any kind of stellar fusion. They're actually now just sort of like corpses of
Mhm.
the original star, because they're basically just giving off latent heat that they had contained within, and it's slowly going away. So over time, they're getting cooler and cooler and cooler. But okay, when you have a red giant star that is in orbit with it, say you have a binary companion, and you have two normal stars going around each other, and one of them expands into a red giant and then shrinks down to a white dwarf. Okay, now eventually the other star is going to go into a red giant stage. And then what'll happen is that red giant might grow so big that the excess hydrogen gas that it's got in its outer environment and outer regions is going to snake on through the center of rotation of that white dwarf and red giant pair, and is going to end up falling onto this white dwarf. All right. And so there is a size of a red giant that after a certain point, that red giant's in a binary system, that red giant can leak gas to another star next to it, and that's when it reaches what's called its Roche lobe,
Oh,
ROCHE. When it fills the Roche lobe, then any gas beyond that can cause it to go through that center of rotation of the two stars and land on the white dwarf. So
huh.
literally, the star can effectively be eating this other star, right?
Well,
Now,
that's cannibalism. Okay.
kind of, sort of, yeah. We're not quite there yet,
Okay.
but it's close. And so when you have two stars, okay, they have gravitational fields, and they form that kind of like a teardrop because of the gravity. They kind of end up being misshapen as they rotate around each other. They kind of do this
Mm.
thing. Now the white dwarf doesn't, but the red giant will have this teardrop shape as it's going around the white dwarf. Right. And that's because of that whole process of stuff. And so the white dwarf is now accreting or gathering this gas on its surface. And a couple things can happen. You can lead to a what's called a type 1 supernova, and that's when the gas on the surface of the white dwarf builds up past a certain mass level, and that mass level happens to be known as the Chandrasekhar limit. That's
Oh,
1.44 solar masses. If you
okay.
get 1.44 solar masses on that white dwarf, where the total mass of the white dwarf is that, beyond that, the star can't handle it. And that's because beyond that, the star is not stable. And what will happen
Mm.
is that leads to a process where we can get a what's called a type 1A. That's Roman numeral one. So it's like an capital I and a little a 1A supernova. And so that is something that can happen with these stars. Now, for denser stars, okay, we could end up having something different happen. So, and that is when we have a two stars next to each other, and one say goes supernova, leaving behind a neutron star. Now, for more massive stars, they go right past the white dwarf stage, like you see there's a white dwarf.
Right.
Neutron stars are a lot bluer, and they're going to be up there, but off the main sequence too. And so they will end up having such a mass that they have that they would also siphon gas off the companion in the same way as the white
Mm.
dwarf. But,
Mm.
they have, like the white dwarf, there's a mass limit to them too. About 2 to 3 solar masses of material can fall on a white or on a neutron star um,
Mm.
before it reaches that magic point. Like that Chandrasekhar limit for white dwarfs, which is 1.44 solar masses, but it's higher than that. It's like 2 to 3 solar masses for the neutron star. And so it may not go supernova in the same way as a traditional supernova because, white dwarfs can explode in a supernova, but when you have a neutron star acquiring mass like this, uh, it reaches something called a Tolman Oppenheimer Volkov limit, or TOV. Yeah, I know. Remember
Well,
that,
that's
folks.
easier to say.
Yeah, TOV. Yeah. Yeah, they reached the TV, and what show was on? I don't know. Right? Right? So the Tolman Oppenheimer Volkov limit is there's this upper limit for a neutron star. But what it'll do is it'll pass through, it'll have so much mass on its surface now. If it's beyond that 2 to 3 masses, solar masses on its surface, it'll go into a collapse and go into a black hole. Okay.
Wow.
And yeah, and so that is really interesting. So unlike a white dwarf, which will explode, a neutron star will continue to collapse into a black hole. And
Interesting.
yeah, and so and we see in the universe, we see supermassive black holes, we see very small black holes, we see traditionally massed black holes. A few tens of masses of stars, of solar masses. Um, and actually, we're missing a certain type of black hole. We don't know of any intermediate sized black holes. We know big ones and smaller ones. We don't have
Huh.
anything in between. There's like a gap. So we knew they were out there. And in a little while, we'll talk about where they are because we found one. Okay. Yeah. So
Ooh.
they're out there. So now the question at this point, then, and I'll get rid of this because we don't need you. Go away. Okay.
Ta-da.
He's gone. See, now you're back. Okay. Ta-da. Yeah. So the question then becomes what when we see that these stars do this kind of thing, we say to ourselves, this happens all over the universe all the time and has always been happening since the
We,
formation of the first stars.
we just
Okay.
assume that, right?
Well, yeah, we do. And we also see it. Now, one of
Okay.
the things that shows us that the early universe was very active is a finding by the James Webb Space Telescope, which we'll see in a little while.
Oh,
Okay.
cool. Cool.
Yeah. And that finding has to do with dark matter, which is kind of cool. So the thing that's important, by the way, this was that accretion model I was showing you
Oh,
about.
yes.
Okay, where you have the white
Very
dwarf
cool.
and the red giant getting literally, uh, you know, reduced to nothing by the white dwarf. So the thing that we want to look at now has to do with this tremendous amount of matter that we don't really see unless we look at the Sky Tour live stream telescopes, shameless plug, and see these dark clouds of gas and dust that
Shameless.
are out there in the universe, right? Like back there in your shirt. Yeah.
Yeah. All right.
There
I'm
it
on
is.
backwards.
And see, it's just a phase. That's my
Yes.
shirt.
Yes. Yes, it
Yeah.
is. Oh my goodness.
I know
Okay.
you have a better shirt on than me. Yeah. So the question is, we study the universe by looking at our solar system, by looking at the Earth first. And then we looked out, we saw the moon. So we looked at the moon, figured out how to get to the moon. Yes, we did get to the moon. I don't care what anyone says. Okay, I'll go to battle with anyone who says that we didn't.
I think we did.
I know we did. Okay. The evidence is unbelievably abundant.
Sat and watched it
And
live on TV.
I did too.
I
Okay.
saw it.
At a time when that couldn't be faked by the network. Today, you could fake it with AI, but back then, there's no way, Um, anyway, there's someone out there going, no, that's not true. Yeah. Take a hike. Okay. We can do with one less listener if you don't want to listen to us.
Mhm.
But the point is, when we look at, for instance, the moon, we then started looking at the stars, and the stars became very, very interesting. Well, I guess you'd say uh, unreachable uh, anomaly, something we didn't understand. And for the longest time, we didn't know what stars are made of until we started looking at spectra, and that was starting in the 1800s or so, and when we actually started to use it for stellar spectroscopy. But we also saw comets. And comets in our solar system, well, you know what comets are. We've seen them,
Mhm.
the bright, shiny head and then that tail of dust and gas behind it, right?
Could be
Um,
green.
yeah, and it can be green. Yeah, they're beautiful,
Mhm.
right? The tail
Mhm.
is usually like a color of sunlight because that's reflected light off of the dust that the comet's leaving behind as the sunlight is vaporizing the head of the comet. Okay, and the green color is interaction with carbon molecules that are on the surface of the comet that are being giving off. Why carbon? Because carbon is the fourth most abundant element in the whole universe.
Mhm.
So it stands to reason there's going to be a lot of it out there, and there's a lot of it in comets, and so that's our basis. We're made of carbon. And I tend to think, as a carbon bigot, sorry, that life is probably based on carbon in the universe and probably not much else. There's
Interesting.
silicon doesn't work. And that column in the periodic table, okay, that column in the periodic table, silicon is just below carbon, and that particular table, which is right here, okay.
Here it
Uh,
comes.
let me see if I can get it. Yeah, there we go. If you look
Woo.
over on the right side there, you see number 8. Okay, sorry, number 6 is carbon. See the C it's sort of green.
Yep.
Okay, yeah, right below it is silicon. Okay, so carbon's number 8, silicon's number 14. Well, that column represents atoms that are kind of most like each other in the way they bond with things, if you want to put it that way. So the next most likely atom that could do what carbon does is silicon. All right, and
Strange.
not germanium, okay, and etc.
Mhm.
Not lead down here at number 82. Okay, I'm sorry, no, that's not lead. Sorry. So the bottom line is that when we look at it was. So when we look at things like there's another one. Okay.
Oh, okay. Yeah.
When we look at this one here, you can see we have carbon, we have silicon, we have germanium, then we have tin, then we have lead, and so forth. Yeah, you're going down that list. They're less likely to be able to do what carbon does, right? So the most likely one after carbon is not phosphorus, is not nitrogen, is not aluminum, it's silicon. Okay, and because that's the vertical column, that's what that means. So when we look at that, what it means to us is that if you look at the way the bonds are made between atoms, okay, one of the things that is true is that carbon can make and break bonds very quickly. As I'm telling you this long, convoluted thing about carbon, your body has probably made and broken about 500 to 1,000 carbon bonds as we speak. So
Hmm.
obviously, that's an ongoing thing. Carbon is very flexible. It's the granddaddy of all elements, as many will say. And so it's probably the fundamental foundation of life in the universe, as the fourth most abundant element. And the third most abundant element, you know which one that is?
There's oxygen, hydrogen, carbon, and nitrogen. No.
No, you're actually very close. The most abundant element is hydrogen. Okay, that was mostly most of it was made in the Big Bang. Very very simple. A single proton, a single electron,
Yeah.
and those couldn't exist together for several 100,000 years after the Big Bang. It had to cool before the electrons, these fundamental particles, could combine with a proton, because the electron's -1, proton is +1 charge. They attract each other, and they can do the thing that protons and electrons do. But
So well.
so wow, yeah. But uh, when you look at the dominant number of elements in the early universe, it was hydrogen, helium, okay,
Oh, helium. That's what it is.
oxygen,
Yeah.
and then carbon. All right. Now, the oxygen and carbon came from stars that lived and died. Stars don't really live and they don't really die, right? They exist and then they don't. Okay. They go through their processes until they can't do it anymore. They run out of fuel. But in that process, they make carbon, they make oxygen, and that gets scattered to the universe. And the universe makes use of that stuff. And so the best use of it is to make us, life.
Yay. Good job,
Yes,
universe.
exactly. Yep.
Mhm.
So that said, when we talk about looking at things in our solar system, we've learned about our life, how we're formed, and what makes us, and we learn about the solar system around us. We examine the planets, we send probes out there, we see comets in our solar system that come from our outer frozen reaches of our solar system called the Oort cloud, OORT. Okay. And that Oort cloud, if a passing star far out, because the Oort cloud is huge, it goes almost halfway or more to Alpha Centauri. Believe it or not.
Wow.
Exactly. And so as a star passes over millions of years, it starts a potential icy body and that Oort cloud on a long millions and millions of years path into the inner solar system, where it may pass by only once and then go back out to the Oort cloud, or may get caught in our solar system in a loop to keep it as a periodic comet that comes back very quickly, meaning within, say, 20, 50, 150 years,
Yeah.
300-400 years. Okay. And those are, there's short period comets and long period comets. And so we see those. Okay. Halley's Comet's a 76-year period comet. Okay. So we have a lot of comets that we know about. Now, many of those shorter period comets, like Halley's Comet, they only go out to about Saturn and come back. So it takes them that long to get out there and back. Okay, so it's a long time. But then every now and then something comes through the solar system that doesn't look like it comes from here. One of these things is not like the other. Remember, one of these things just doesn't belong. Well, exactly, right? That's exactly right. So in this particular case, we saw Oumuamua first. Now, to be honest, we didn't see Oumuamua. We actually caught the object after it had already gone past the sun and started speeding away. When it's out here is when we saw it. We didn't see when it was over here.
Wow.
Okay, we saw it when
That's
it was
kinda
going away.
scary.
So
We didn't
it is,
see it.
because he could have hit us, and then
Yeah, it's a
you
minor
know,
detail. Yeah.
we'd be like flat as a pancake, and that wouldn't be good. So, but then we didn't have a lot of time with the Oumuamua. Then came the comet Borisov, which was another comet that came from a different location than we had ever seen, and that was a comet that ended up being fairly quick in our solar system. Again, didn't have a whole lot of time with it, and so we're kind of on the lookout by then. And so along comes a spider with this 3i Atlas. Now, 3i Atlas was fascinating because, you know, we have to admit, interstellar objects that come from far, far away, okay, beyond our solar system, are always very interesting to us nerds. I mean, astronomers. And I guess I have to say, when we look at 3A Atlas, one of the things that we had to do was to try and explain some of these many anomalies that it showed us. Now, one of the problems is that, of course, when you have a leading astrophysicist in Avi Loeb at Harvard who looks at it and says, and very rightly said, there are a bunch of strange anomalies. He's absolutely right. He's not been wrong ever. Okay, about all the
Ever.
things he said. No, not really, not at all.
That's pretty
Okay,
impressive.
he basically said we can't ignore all of these very strange anomalies because some of them point toward intelligence. Is it intelligence? And all he's saying is we can't ignore the possibility. And meanwhile, he may know or suspect that it could just be an ordinary comet, but we can't ignore the possibility that it's not. And so what he does is he went after trying to figure out whether it was a comet or whether it was an extraterrestrial craft, a probe. Why would that be so outrageous? We're thinking of doing the same thing.
Well, we've done it, haven't we?
Yes, we have. We have two of them, Voyagers, which are now headed or have left our solar system. Yeah. Well, just because we've done it, 30 years ago, and it's just now just reaching the outside of our solar system, it doesn't mean that another civilization couldn't have done this billions of years or millions, hundreds of millions of years before us, and ended up possibly sending a probe to here. Now, 3A Atlas, okay, one of the problems with 3A Atlas is that it seems to be pretty old. And if 3A Atlas was sent out into the universe from, say, a home world, let's say it was a probe, the problem is it was probably, according to our understanding and reverse engineering of its path, at least 7 billion years old.
Oh my goodness.
Now that's a problem, isn't it? Because our solar system is how old? 4.6 billion years.
Oh, solar. I was thinking the universe. Yeah.
But our solar system is only 4.6 billion years.
It's young
in age. So a 7 billion year old probe, it's not going to start off and go in a direction where we will be, right? They would want to send it to where we might be, right?
But do you think they're still waiting there after 7 billion years to see what signal comes back?
And that's another problem. Okay, they would have to
Ah,
have some other technology. Now, let's be honest. A civilization a long, long time ago could have sent a probe out, and once it went through another star system and started the long transmission back to its original creators of the data, it could have left that solar system or that star system and winged its way and found us. There's no, and really, when you think about it, in a civilization that's not that's more advanced than us, but not as advanced as the very high tech civilizations we think about. Um, well, that could actually happen where they send out a probe that takes a million years to get to us, right? So,
yeah. Well, they must be out there. Is that Three-Eye Atlas? Is that what that is, Mark?
well, no, I just think you have to wait and see.
Ah,
Um, but
hmm.
see, one of the things that it had was a bunch of anomalies, and among the anomalies it had was initially they saw a high nickel content. Now, what does that mean?
Isn't that normal for like comets or meteorites and stuff? Or
Yes, it is. But um, we have what's called a nickel to iron ratio. Nickel
ah,
in our periodic table. Here we go with that table again. Oh
ah,
no, don't do it. Don't do it. Ah.
ah.
Well,
Hmm.
if you look over here, let's see. You have iron at 26,
Mm-hmm.
okay, and then you have 28. You have nickel. So when iron is formed and nickel is formed, the we go by taking number 28 and
Okay.
pairing it to number 26. Iron and nickel are combined, are compared to.
Ah,
So it's a nickel to iron ratio, Ni to Fe.
okay.
Okay, so
Mm-hmm.
that's how that works. So the nickel to iron ratio on ordinary comets is a very low number. It's actually there's typically more iron. All right, so it's a 0
Okay.
point something number. But with Three Eye Atlas, that number was something like 130, meaning
Ooh, big
way more
difference.
nickel on top of the equation and little on the bottom to make it smaller. So now, how could that happen? And that's one of the things that's been talked about as the nickel carbonyl trap. Okay, and what does that
Oh,
mean?
it's
It
a trap.
means it is a trap because the nickel to iron ratio is skewed, and we don't know why or didn't know why. Now we think we do. Okay,
Oh.
yeah. So
Mm. Hmm.
when you have nickel and you're in a molecular cloud, a comet, a distant comet where it's very cold, your nickel atoms could combine with carbon monoxide atoms, which is carbon, C, and O, right? So,
Okay.
okay, that's it. Carbon monoxide. Okay, carbon monoxide. Breathe me, you die.
Okay. Yeah.
Okay. So, but and so you get a nickel carbonyl atom. You get a nickel with 4 carbon monoxides. Technically, it's nickel tetracarbonyl. Okay, and so you have a nickel atom in the middle and 4 carbon monoxide molecules on the outside.
Okay.
Okay, and that's a carbonyl trap. Basically, the nickel's trapped by carbonyl
Okay.
by these carbon monoxide molecules. Now, the iron is trapped by 5 carbon monoxide molecules, and that's iron pentacarbonyl, penta for 5. Okay. Now, the thing is, uh, when the comet's coming into the solar system, it's getting heated up by the sun.
Right.
Right? And the sun heating the surface of the comet is going to cause things to happen chemically. You'll start to see a glow. You'll start to see that greenish color show up. You'll start to see other things happening. And among the other things that happens is the temperature reaches 100 degrees Fahrenheit at certain points on the surface of this object coming in. And that 100 degrees Fahrenheit, okay, it's actually just over 100. It's like, I think it's 109. When that
Slight change.
happens, a slight difference, all
Mhm.
right. The nickel carbonyl, the nickel with 4 nickel tetracarbonyl with 4 carbon monoxide molecules, uh, vaporizes and releases the nickel. The iron is still bound up with the pentacarbonyl because it doesn't do anything at 100 degrees Fahrenheit. So looking at the early views and spectra of 3I Atlas, we saw a tremendous amount of nickel and very little carbon. However, as it got closer, the surface of the 3I Atlas was heated up to the point where the iron pentacarbonyl vaporized, releasing the iron. And then that nickel to iron ratio started to get smaller and smaller and smaller and reach relatively normal levels comparable to what we see in our solar system. So the initial statement of like, oh man, there's nickels. Well, we use nickel to make our spaceships and the hulls and maybe
And nickels.
nickels. Yeah. Unfortunately, fell down to the wayside because there was a much more practical explanation for it at that point. We actually see that the iron to nickel iron ratio, started coming up.
And that makes sense, right? So,
yeah, and that's the carbonyl trap. That's the thing where, the carbonyl doesn't release the elements until certain temperatures are reached. For nickel, it was 100 degrees Fahrenheit. For iron, it was 200.
It doesn't seem very hot. I mean, it's hot.
No, that's right. But I mean, when everything is formed in deep space in the cold, as you'll see with this object, then that means 100 degrees Fahrenheit is unbelievably hot for a comet made of such volatile ices like like carbon dioxide ice. So a lot going on. Now, the other thing beyond the carbon and the nickel and iron mess was the fact that it had these anti-tails. It had multiple jets aiming toward the sun of material. What were those?
Towards the sun?
Yeah.
Towards. Okay.
We see tails facing away from the sun. Now, in a perspective world, anti-tails are formed by comets all the time. Okay, I've got photographs of them, like Comet Tsusen Atlas. We actually took pictures of the anti-tail. What that is the comet has a long curved path. And as it's going around in a curved path, it can get to a certain point where the previous tail that it released back here is visible in front of the comet out here. Okay, and then you see the other tail here. Right, and it's a perspective effect. But that's not what was seen with 3I Atlas, and that's what made it so different. I remember saying maybe it was just an ordinary anti-tail. In fact, that was incorrect. It wasn't. There were actually a 7-jet anti-tail on this, meaning there were 7 active regions on the head of that comet or the head of that object facing toward the sun and ejecting material in the direction of its motion. Now, that was kind of weird, but I began to think what could cause that, and I started doing some research and excuse me, and realized that what could cause it is the fact that this comet object, 3I Atlas, also had a huge abundance of carbon dioxide on it. Now, the content was way higher than normal carbon dioxide ice content. And so if you're getting that close to the sun with a CO2 ice on your surface, it's going to sublimate. It's going to go away. And it might do it violently. And it may do it only on the side being heated the most, which is the sunlit side. So any jets, I predict in my mind, I was thinking, hey, that could cause this. So yeah, and in addition to that, okay, when it got closer to the sun, in support of that idea, as the comet got closer, I keep calling it a comet because that is the final disposition. I think most people know that.
We do now, at least.
We did before too. As it got closer to the sun, what ended up happening was it had this much higher brightening than expected for a comet. Okay, it was a extreme as a perihelion when it got close to the sun. Close, apogee is away. So perigee is close, apogee is away. Okay, farthest. So the perihelion distance, the closest to the sun, as it went by the sun, it was brightened way more than ordinary comets in our solar system. And most likely, this carbon dioxide ice was the culprit in part. And the reason was because as it sublimated off the surface, again, where did it all come from? Where did it get so much carbon dioxide? That's another discussion. But it was there. And because it was there, as it sublimated, it released all this additional dust and just filled the entire, uh, uh, I guess, area around the comet, right? The whole coma, the atmosphere, so to speak, of the comet was much more dense and bright. And this is because of all that dust that was now released as the comet began to
Wow.
get rid of the carbon dioxide ice even more rapidly than it had. So that was pretty cool. So the high abundance of carbon dioxide ice is what did it. And that's what we call dry ice, right?
Oh, cool.
Hmm.
Yes, that's
No.
true. Duh. Yeah.
Yes. Any questions, class?
There was a question of someone,
Oh,
um, how I think they were talking, how do you determine the age from long braids?
oh, good. Thank you. That's a really good question. First of all, thank you, long braids. Um, when you look at a comet, one of the things we have to do, first of all, knowing that it was interstellar, it has to do with reverse engineering its path. We see that it did not come from the Oort cloud; it came from farther away. And so, reverse engineering its path, we can tell that it had to have originated in another star system. So already we know that at the expected cometary speed, like we saw it coming into our solar system, the sun accelerated it, okay, to well above 130,000 miles an hour, if I recall. And as it
Woo.
did that, okay, yeah, it's fast, okay. But as it did that, it kind of helped us figure out that it was something from another star system. And so when you reverse engineer the locations and the distances of the nearby stars throughout time, we could kind of sort of interpolate that it was between 7 and 8 billion years that it may have taken to
Amazing.
make that journey at
That's
the
amazing.
interstellar speeds it was traveling. Yeah, and that's what's cool. Now, I'll tell you one thing: it's possible that this object came from a red dwarf star system, which is kind of neat.
Mm.
Now, red dwarfs, the other end of that OBAF GKM scale, those are the
Right.
M's, little tiny stars. They're only slightly bigger than Jupiter, so they're very very
Oh,
cold environments, right? And so
it's
the
big.
stars themselves are hot, and to have planets in a habitable zone around one of those stars, you literally have to be closer than Mercury is to the sun, and you can actually have habitable zone planets, uh, three of them in the TRAPPIST-1 case, which is another
Mhm.
dwarf, circling, and possibly life there too. But in the outer reaches of stellar systems like that, it's so cold out there that if for some reason another passing star ejects it or causes it to go on a long interstellar journey, it's going to go through dark dust clouds. It's going to go through all kinds of stuff where it could acquire CO2, carbon dioxide, or chemically alter carbon compounds into
Mhm.
CO2. A lot going on there. One of the things, um, yes, that 3i Atlas also did, or also showed, one of the anomalies was it had this extreme deuterium enrichment. Now, what is deuterium? Deuterium is hydrogen with a neutron in its nucleus.
Oh,
So
okay.
remember, hydrogen's a proton and an electron. Okay, but if you have a deuterium, that means you've added a neutron into the nucleus with the proton. So you have a proton, a neutron, and then that one electron going around. Now that's okay. Most of the deuterium that was in our universe now was originally made in the Big Bang. Okay, almost all of
Wow,
it. Okay, and so that's another hint
amazing.
that this particular comet was made in deep space, or came from a very deep space location, um, because the deuterium in this particular comet, right, was 30 to 40 times, okay, the amount that we would see in cometary compositions from our
Wow.
solar system. Okay, 30 to 40 times. So that's a really interesting finding, you know, and that kind of content can only form in the darkest and coldest regions of space, and that's what was important about this. So what do you mean by cold? Okay, below 20 degrees Kelvin, that's minus 424 Fahrenheit. I don't think a fur coat's going to help you much.
No.
Okay, no. All right, it was essentially acquired by the core of 3i Atlas. All right, but the composition of 3i Atlas is showing us that it had to have formed in a dark, cold cloud of interstellar dust or in the outer regions of a star system with a red dwarf star, like I mentioned. So, having this extreme isotope of hydrogen in it was an oddity that we couldn't initially explain, and only now we have just theories of, that it formed in a distant star system, right? And then, of
So,
course, yeah, go ahead.
just a quick question. It's a silly question, really. When you're talking deep space, we're still talking our galaxy. We're not talking by
Yes.
looking at another galaxy or between the deep space between galaxies, right?
No, we're only
So,
talking about stars kind of next door to us, even.
yeah,
And it could still
real
take
close, right?
a long time to get
Wow.
here. Yeah.
Thank you.
No.
Yeah.
And then the other thing is, in that long time to get here, somehow this object found a way to come in only 3 to 5 degrees off of our equatorial plane, in our ecliptic plane, in our solar system. So it came in almost at the level of our
Wow.
planetary
Coincidence.
plane. Yeah, that's exactly it. Is it a coincidence? I mean,
That's probably one of the other flags, that
it
they were
is.
thinking about.
You're right. It is. Now, on the way in, it passed Mars. It rounded the sun and it passed Venus. Then on the way out, it went by Jupiter. So it almost seems planned. It
Yeah.
almost seems like it could have been an intelligent, I guess, an intelligent thing, right?
Design. Well, it's a good show to see all of that. So,
It sure is. And, this, for instance, this is a photo that we took
pretty.
with SkyTour live stream cameras after it rounded the sun and went past Venus.
Wow.
And you can see that green color you commented on
Yes.
earlier.
Mm-hmm.
Yeah. And that green color
Pretty.
comes from carbon compounds that are interacting with sunlight and causing it to, brighten up and give off a green light. That's what you see with that. It's the element, the compound cyanogen. All right. You see a compound of carbon bonds with carbon, two carbons, okay, bonded to each other. I'm trying to get it. Two carbons bonded to each other. Very good bond. It'll make a green glow when it's ionized and the electrons jump back into the molecule. They actually give off green light. Same thing with cyanogen. When the cyanogen is broken apart, the cyanogen is a carbon and a nitrogen in a pair. Okay, when it's broken into the radical CN, okay, that's an ionized object. When it gets its electron back, it's going to give off green light. So cyanogen does that, carbon does that. So we noticed in the 3i Atlas shot that, yes, we're seeing that green. Okay,
That's really cool. That's huge too.
Yeah, it is, and it's that coma, that glow around the core, is millions of miles across. Okay, because it's so far away. If it was a lot closer, it'd fill the sky. You know what I mean? So that's pretty neat.
Very cool.
So, yeah. So now, one of the other things too is we're gonna just sort of change gears a little bit here.
Okay, we have just a 3-minute warning for you too.
Yep, I got you. We're gonna just start. I did want to mention, so today's show. Here's the leader for today. 2 hours on the bleeding edge of the universe. Okay, we're going to talk about black holes, Mars anomalies, dark matter, and strange new worlds. And so far, we've talked about 3i Atlas, so we've got a long way to go.
Those were neat planets you had in that picture.
Sorry. I know, we had quite a few in there, didn't we?
That was pretty cool.
Yeah, that's neat. And those mountains on the planet at the lower left, completely impossible. But hey, you know what? It's okay.
Oh, you never know.
I just thought it was cute. I just thought it was cool. Anyway, so that said, we are going to spend some more time talking about the James Webb Space Telescope next. And the James Webb has done something that's never been done as well as
Mm.
the James Webb can do it. And that is when we look in the universe and look at galaxies,
Mhm.
we see that galaxies that rotate, okay, they seem like they're rotating as solid disks more than whirling stars, where the outside stars are spinning a lot slower than the inside stars. The
Go real
inside stars
fast.
are going faster than the outer stars, but
Mhm.
not in the expected amount. Okay, it defies the laws of kinematics, the way it's in celestial mechanics, the way it's rotating. These stars out here are moving faster than they should compared to the stars in
Hmm.
here. Now, you notice the galaxies have spiral arms and they're swept out, aren't they? They're swept out
Right.
behind, they swirl around. Well,
When you
they're
spin.
swept out. They've been there for billions of years. So they should all be wound up by now, right? Those spiral arms should have wound up into a tight ball
It's a
eventually,
slow process.
but they're not. And that's something that could be, there could be another form of matter we don't yet understand until now, okay, that was holding the galaxy's mass on the outside, moving in a sort of an amount that would allow the outer mass to keep up with the inner mass a little bit. There's still differential rotation, it's called, where the outer is moving a little slower, but it's been helped along by stuff called dark matter. That was the theory.
Oh, love it.
Yeah. And so
Interesting.
that's what we're going to talk about.
I want to know what
when
dark
we-
matter is. Mhm.
Yeah, we're going to talk about that when we come back. What's that? Does that sound good?
Sounds great.
I know.
Don't leave us in the dark. Come back. Tell us.
Oh, that was
Oh, that was-
good. That girl. That girl. All right, guys. You know what? We'll be back in just a few minutes.
Patriox oxygen water addresses a condition called hypoxia, which is insufficient oxygen in the cells and tissues. The fact is that hypoxia triggers 90% of all chronic conditions, including circulation issues, low oxygen levels in the blood, and more. By drinking Patriox oxygen water, you can restore oxygen levels in the body, restore energy, reduce age spots, and renew stem cells. Now, as an UNX listener, you can get 10% off of Patriox Ultra High Oxygen Content Water at patriox.us/discount/UNX News, or check the shop page at UNX Network for more information.
I guess we're back.
Hey, glad to be back.
Yeah. So, interesting thing happened. And just as we went to commercial, the phone buzzed, and it was a friend of mine I haven't talked. Used to work for me here, Matt. I haven't talked to him for a long, long time. Then he called to tell me a couple things, and it was just a quick call, and it hung up literally just as we came back. It's almost like he was watching, but he wasn't. It's kind of cool. Anyway, it's just a interesting coincidence, right? So this dark matter thing, interesting, because up to this point, and the Hubble did this earlier, but it didn't do it. It didn't do it with 100 times the capability of the James Webb. What happened was, when you consider that when you look out in the universe, there's trillions of galaxies, aren't there? There's 2 trillion additional galaxies besides our own, and these distant galaxy clusters. Sometimes there is a cluster in the foreground, and there's a distant cluster behind them, and the light coming from this distant cluster can be bent by the gravity of this cluster that's closer. And that's called a gravitational lens, okay, a gravitational microlens. Well, the James Webb looked at 800,000 galaxies, okay, just 800,000 out of the 2 trillion. And it found that 250,000 of them were gravitationally lensed. Their paths were curved, their shapes were different. And this was the foundation for a study to try to visualize dark matter, because in some cases these galaxies were lensed by material that wasn't there. Okay,
Huh?
and that is then what happened was they produced a map of these areas where the mass wasn't there. And in this map, I'll show you the brightest of the blue areas that you'll see are the highest concentrations of dark matter. Dark matter
What?
visualized. There it is.
What?
So, yeah. Now those are stars and galaxies that you see here. The stars have the little diffraction on them, and the galaxies are all the other spots. And you're seeing that areas where there's dark matter, clumps. All right, and they call this the scaffold of the universe. This is actually the actual the material that is actually fundamentally building the universe. This is how the universe is built, from this material that you're seeing right here. Okay, all these little blue areas. The brightest blue are the clumps. Notice how they're little spherical clumps. Okay, of dark matter. They're not like just long, snaky things. There's softer areas of blue, which is additional dark matter. But think about it. This is, we're looking at the cosmic scaffold, the actual way in which the universe is being held together.
Is that
And
like that webby thing, Mark? That
yeah,
web kind of looks like a thing of cheese, Swiss cheese.
Well, I mean, I guess, yeah, except the holes are dark matter, right? That's
Okay,
it's
yes.
random.
Well, yeah.
Yeah.
We didn't know if they were dark matter, right? And you're saying we can now find it? Is that what
Yeah,
you're
well,
saying?
the Hubble did a similar study, but the resolution was literally way less, and the James Webb is 100 times more sensitive and capable. So this is a far more detailed image of dark matter in this particular region of the universe. Obviously, this is not a full encompassing thing; it's just a region of space that it focused on. And in that region, there were 800,000 galaxies, and of them, 250,000 were being lensed by that matter you see right there, that dark matter. That's pretty interesting, isn't it?
Oh, it is. The texture of it is what's so strange. Like you said, it's not snaky. I wouldn't have expected that.
Yeah,
And
they're clumps. They're clumps, spherical clumps of dark matter with some. You can see some lighter blue clouds in there. That's not Milky Way. That's actually dark matter map.
do you think it's
Because
gravity then that's clumping them? Does
yes,
it have does it have
the
gravity? And
yes, the dark matter, which
that's
we
why they're
cannot see
Mhm.
yet, okay, is lensing or causing the misshapen galaxies to show up, because there's nothing there to cause it other than dark matter. And so when you're looking at the dark matter objects or locations, you're literally seeing through reverse engineering. You're seeing the locations based on the gravitational lensing of the galaxies in the field. You're seeing the interpreted locations for the densities of dark matter. And the 2 densest regions are the one right up there at the top,
Right.
One over there on the far side and the right side, just above your,
Mhm.
just
Right.
above.
Wait.
There you
Wait.
go. You'll get there. There you go. There you go. That's right. That's right. You get good at it. You get
Backwards.
good at it after a while. Yeah.
That's funny.
Yeah. So anyway, oh, sorry about that little earthquake. I was
Oh,
I was awakened the other night and the other morning actually by a small earthquake here in Connecticut.
oh, my.
Yeah, my bed started going bam, bam, bam. It's like, what the heck? I wake up, and then it was like 2 seconds long from when I woke up, and then it stopped. So I don't know if it went longer than that. But everybody I know was driving at the time, and they didn't feel it. I was the only one that felt it because I'd worked late the night before on a Navy model to get this Navy project done. So I was still in bed, and I felt it.
Wow.
So yeah. Anyway, so this
That's
dark
cool.
matter map then is sort of visualizing where dark matter is in our universe. And in fact, it's showing where the distribution of dark matter in this particular field of view right here. So this
Right.
is rather interesting. And and so by studying the lensing with these 250,000 galaxies, they were able to reverse engineer the locations of the concentrations of dark matter. Now, James Webb's was 100 times more capable, as I said, and they're literally, as I said, seeing the invisible scaffold of the universe, how it's made. I mean, I think that's pretty cool, don't you think?
I think it's amazing. Do you think those move? I mean, I assume they're going to be studying those little bright spots and see if they move over time or change shape, or not necessarily shape, because
Well,
they seem to be circular, but
well, we would need a lot of time because they're spherical, probably, and
yeah.
they're three-dimensional, and we'd need a
Right.
lot of time to actually see what they do. We'd need millions of years to actually watch
Oh,
any changes occur. They're not going to change moment to moment, year to year.
interesting.
Yeah.
One of the Charles had a question, Mark.
There's Charles Smart. How you
Yeah.
doing?
So how much does the dark matter, what's the density of the dark matter? Do they know?
The density of dark matter actually is, in terms of visual, the lower densities are the areas that are lighter blue and more cloudy. The concentrations are the spheres, and as far as the actual density, I don't know that answer, Charles. I don't know that answer because this map here just came out, and I don't even know the units for this yet. But I had to show you because it's so cool.
Is this the new astronomy field? Is this something that people are just going to focus on?
No pun intended.
Yeah.
Yeah, no, this is definitely going to be one of those. I think one of those cases where we're going to be looking for other concentrations in the same way, and we will find it. We will find more concentrations of dark matter. Again,
that's cool.
What's interesting to understand is that we're looking across the whole universe at all these galaxies, and if we see lensing going on, micro lensing, where the actual galaxies are having their shapes distorted a little, and we know it's not from galactic interactions with other galaxies, then we know that it's being lensed by something that we don't see. And so if you look around that object and you find others, you find the complementary ones. If like this one's curved this way, okay, then maybe this one's curved this way. And together they actually would form the lens, the actual round shape of what's expected with a lensed object. And so by drawing all those correlations, you can say there's something there that we cannot see that is causing the light from that distant galaxy's cluster of galaxies to bend. And that's got to be something that we can't see, and that only something that we know of that we can't see is dark matter. And so that's probably what we're looking at. And so it's actually really cool that we're seeing this. And I was so astonished by this map. I was just blown away, to be honest. It's the coolest thing.
It is. I could stare at it for a long time. Just
okay, good. You do that, and I'll be right back.
I could. Yeah, that's amazing.
So yeah, those, now you'll see there's some black areas in there, and I'm not sure what those black spherical areas are. Those aren't concentrations. Those are a dearth of concentration.
It's dust.
But I'm interested in knowing what makes those as well, because in the upper right there you have one very, very high concentrated area, okay, and then right to its lower left you have a dark spot indicating a very little
Yes.
concentration of dark matter, and I don't know what that is. What is that? You know, that's another thing that I don't understand. Now, is that a artifact of the way it was made? It's possible. I don't know, but it's pretty interesting nonetheless.
But don't you kind of teach us too that that's clouds of dust that's blocking the light behind it from coming through? But
Yeah,
why would they be round?
yeah.
Or
Except what's different here is in the wavelength that we're looking at here. Um, we're looking at a different altogether thing. We're not looking at dust. Okay,
okay.
we're
Huh.
looking at we're looking at merely gravitational lensing. We're looking at the distortions of galaxies. We're
Okay.
not looking at dust. Dust tends to be, you know, distributed throughout the galaxy. Some more dense concentrations, some others. But the gravitational lenses occur well beyond our galaxy. Okay, we're looking at gravitational lensing coming from. Now, it occurs in our galaxy, but for these kinds of studies here, we're looking at distant lensing caused by things. Now, if we have a very, very massive star and there's a galaxy cluster behind it, then that massive star, yes, and the star in our galaxy will lens that galactic cluster to some extent. But when we're looking at a shot like this, where every dot you see in here is a galaxy, and where you see, except for the stars that have the spikes on them,
Right.
okay, there's only a few of those, right? And now you consider that all those galaxies are distributing or exhibiting some form of distortion in a symmetrical way around those blue dots. You then will interpolate those blue dots as being a concentration and thus show it as a blue dot. And that's what it's doing.
I
You know,
see.
yeah. And but I want to know what the black areas are. That's something I'm going to pursue to find out what's going on there. Not to beat that one to death, but I beat it to death. But it's really cool.
It's
So
an
James Webb is making strides.
exoplanet. It's not an exo. It's an exo. Um, dark matter.
Exomatter.
Exomatter. Yes.
That's and watch now they'll use that. And they'll say, darn it all, that was Tara thought of it.
Yeah.
Yeah. Yeah.
That's
So
really
that's
interesting. Thanks for showing.
Yeah, no, it's a really cool thing, you know. Let's see. Let me bring this one up.
Oh, that's good.
I think you meant occurrence. Can you speak to the occurrence of dark matter and regular matter in the same proximity? Yeah, well, I mean, dark matter has a capability of doing gravitational attraction. So we see that with galactic rotation, where you have galaxies where you have a lot of regular matter, and then dark matter halos apparently around these galaxies that are causing the galaxies to rotate more as a solid disk, as I mentioned earlier. Now, they do differentially rotate, so the stars on the outside will lag behind over time, but not enough to have not wound up the galaxies for the last 13.8 billion years that they were around or so. So um, I think that the one thing that's important to understand here is that regular matter can be affected by dark matter, and we're seeing that the galactic rotation is an example of regular matter being affected by dark matter. Okay, and so that's an example of this exact thing happening.
Cool.
Let me know, Dan, if that answers your question.
Yeah. Thanks,
You
Dan.
know,
Mm-hmm.
and I knew you meant occurrence, not the other one. That's fine.
Spell check.
Yeah, yeah, spell check. What does it? It doesn't matter. I read between the lines.
It
I'm
doesn't
good at
matter.
translating. So all right. So now let's look at something else that the James Webb has done that is really cool. The James Webb has done this. I would have to say, most incredible thing. It's actually found now. It imaged a group of galaxies that are sort of in collision called Stephan's Quintet. Okay, now that's a fairly well-known quintet of five galaxies that are kind of all interacting with each other, and those are a couple 100 million light years away, or whatever, maybe less. And these galaxies are well known to us. They existed for a long time in the universe before they interacted with each other. But What if I told you there's another quintet of galaxies that James Webb discovered that's
Oh,
doing exactly the same thing, but only 700 million years after the Big Bang? Now, what does that mean? It means that fully formed galaxies, okay, with their spiral arms and so forth, all already in place,
mm-hmm.
uh, were interacting with each other all the way back to just 700 million years after the Big Bang. Now, that's what happened, and this is that image. Okay. Now, it doesn't really look the best because it's a very distant group of 5 galaxies. Okay. And you can see them there. All right. And you have elliptical galaxies, ELs, and you have regular
Mm,
galaxies. And these galaxies are all interacting with each other. And the reason we know that is because we use different filters to look at this data. And when we look at this, when we look at the data, okay, down here, you notice it says F115W. What does that mean? Okay, F
Watts.
stands for yeah, right there. Watts, I know, right? It is the international symbol for watt, but that's not what this is.
Oh, okay.
Um,
Sorry.
F means filter, and 115 means 1.15 micrometers, okay, or 1,115 nanometers. It's a frequency, a wavelength, okay.
Okay.
So, and it's the W means wide. Now you have wide, medium, and narrow for the profile, and this is wide, okay. And is what this is what was found, and the interesting thing, and this is known as the JQ, the JWST quintet. And when they actually used another filter set, which showed the doubly ionized oxygen level inside this galactic, I guess should say, conflagration, okay, collision, all right, 700 million years after the Big Bang, it looked like this. So
Oh,
on the left is the original one, but now on the right, notice the green. The green is the oxygen 3. Now, doubly ionized is O3, O with 1, 2, 3. You
one,
see it
two,
up in the upper
three.
right corner there.
Yes.
Okay. Now, reason why we say doubly ionized, not triply ionized with the 3, is because at the base state where you have where an oxygen atom has all of its electrons, that's O1, so Roman numeral 1. And we leave off the 1 when we talk about oxygen. Otherwise, we'd have to say there's hydrogen 1, helium 1, blah, 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 blah. Okay. But for convenience, we just say oxygen and not oxygen 1. Right.
Okay. Oh,
If you ionize it once, it's O Roman numeral 2. O2. So it's been singly ionized, and 1 electron has left the atom. If 2 electrons leave the atom for a period of time because they absorb some ultraviolet energy, then it's called O3, like you see here. So O3 is just 2 electrons that have been temporarily, activated or energized to leave the atom temporarily. When they
mm,
come back into the atom, they give off light, and that light is this characteristic green color that you see.
okay. Pretty.
Okay,
Yeah.
so that's how that works. So in the same way, we're looking at 2.7 f 2.77 micrometers, micrometers, 3.56 and 4.44. Okay,
Okay.
so
Yeah. Big
2770
difference.
nanometers, 3560 nanometers, blah blah blah. So we're actually looking in these different wavelengths to see these objects, and we're looking at this beautiful oxygen 3 and hydrogen beta line here, which is this giving us this beautiful color that we're looking at there.
Mm-hmm.
Um, and you can see how it's all connected. You see how in the left image, you could argue, well, how do you know they're interacting? I mean, the ones at the top left could be a little closer. The one at the bottom right could be way far away.
Mm-hmm.
We know because when we actually do the study on the right, we can see that they're all sharing material. So they're actually very close to each other. So
Mm,
what the James Webb has found is a 700 million year after the Big Bang collision of 5 galaxies. It's a gigantic, very tight collision.
Wow.
And so the problem with this is that the standard model that we understand of cosmology says that early galaxies should be tiny and lonely and isolated. Instead, the James Webb Space Telescope found the five-way cosmic demolition derby.
Hmm.
Okay,
In just
um,
700 million years, right? That's
after the
nothing.
Big Bang, yeah.
Yeah,
So
that's
that's
nothing.
like it almost should not exist,
Something's
right?
wrong. Yeah.
It almost should
Mhm.
not exist. Yeah. So yeah, that's the really weird thing here, and so I think that this image kind of tells that story. And
That's
so
cool.
that yeah, it's just astronomy is just moving at leaps and bounds. You know what I mean? And it's like I don't know what to say about it other than I just can't take my eye off it. you
Oh,
know, right? Yeah.
there's lots to
So
see when you look up.
there is a lot to
Lots to
see when you look
learn.
up.
Yeah.
Yeah, yeah. Now, what I'd like to do here next is to give you all a Sky Tour live stream update. Okay. It's time to talk about the future and where Sky Tour live stream is going. No, this isn't the kiss of death. No, we're not stopping. In fact, it's all good news. We're moving faster than ever before. As a matter of fact, recently a scientist, and I'll be talking a lot more about him once this all happens and it's come to fruition. But he has donated to us, which we haven't yet received, but we're going to a telescope like this one. This is a
Ooh.
14-inch
Wow.
diameter Celestron ultra high. Basically,
Wow.
it's called it's an HD telescope. It's called the Edge HD. It's actually the best of the best that Celestron offers in this particular category. It comes with that mount. It even comes with that tripod, but we're going to put that on a pier so we don't have to worry about the tripod. And so that mount and telescope right there are coming to us, along with all the cameras that he
Oh
has for them,
my.
along with a wide field system. So we can actually look at the wide field
Great.
under the Benson skies. And we're actually getting another building in Benson to put this in. So we are actually moving quite a bit
That's
faster than
awesome.
we. Yeah, and
Yay, hold on.
yeah, no, this was great. Now the reason that we're getting the donation is because he said he can't use it very well at his location. Not because he's old or anything. He's not. He's actually bounces around probably more than me. But he basically doesn't have the skies for it. He'd
Mm,
rather see it be used under a dark sky, and so that's why. So we're excited. We're cautious because, until I knew that it was pretty much guaranteed, I wasn't even going to say a word. I've said it to a few people, but I haven't really said it. But now that when he messaged me the other day, he's going to actually make sure that this is not just a vapor promise. He's actually doing it.
Yay.
So
That's great.
yeah, we're gonna cover the cost of the shipping to get all the equipment created
Fair
in
enough.
wood
Hmm.
crates and sent out to our location, where we're going to take it down to Arizona and have them do a once over on the equipment, make sure everything is in order, and
Perfect.
then we're going to install it down in Benson. And now we're just waiting for the Benson second building, number 2. We're going to have 2 observatories in Benson, okay, with 3 telescopes. So there's 2 in Benson A right now, and then we're going to have 1 in Benson B. And I'm pretty excited about that because
Yeah.
we're going to be able to then take our telescope that's currently the wide field system in Benson A and convert it to a spectroscopic system that will actually use our new spectroscopic system that we're
Oh,
getting from Shellyak systems. And that's going to be
wow.
even better. So
Oh,
we're
that's
looking
amazing.
very forward to this.
And then you're going to have them both, all the telescopes running at the same time when you have the roofs off at night.
Of course.
Yeah, I figured as much. Okay.
Yeah. And why not? Of course. And we did leave the Sonoran site, Sonoran Desert. And it's sort of like, it's too bad we have to leave. The owners of the land are are not going to be going out there anymore, apparently, and that's going to make it harder for us. And I can't have this much equipment in a location that could be at risk, because there won't be a lot of people there all the time anymore. So that said, we moved out of the desert, which is fine because we had to travel on paved roads and then go about how many miles on dirt roads? I mean, a long distance on dirt roads, miles and miles on dirt roads until we got to the observatory
horrible dirt roads.
And Tara's truck, the Terramator, okay, is the one that sometimes had to go make those journeys along with Marianne's vehicles. And it's wear and tear on the vehicles. And there's been a couple times when we've gone out there and we couldn't pass. So we had to go around. I remember being on one trip. You've been on a couple where the roads were flooded out, right? And you couldn't turn around and go in from a whole nother direction. That added an hour to your trip.
That's because there's a wash that goes through that desert. So
yes, the Hassayampa River.
Yes, it does.
And the Hassayampa can sometimes be flooded, and you see the gates are out closed. You go, I don't have a boat.
I think I'll go to Wickenburg and go in that way.
Now you have to go up through the city and back down around and add an hour more to your time.
Yeah. It's pretty though. It's beautiful. It really is.
It's beautiful, yeah. And you've taken some beautiful sunset shots, by the way.
Oh, yes.
In your vehicle. I remember you sent them to me.
Just gorgeous.
Yeah. Really pretty. But hey, the bottom line is that now to do maintenance, instead of driving 220 miles down from the Sonoran site down to Benson, it's a little different now. Now to do maintenance, it's a 4-foot walk from the one telescope to the other. And then we're going to have this bigger scope, and that'll be a 70-foot walk from these two telescopes.
I don't know. Gosh, can you believe that? That's awesome. That's so cool.
So I'm pretty happy about that. Pretty pleased. I'm not happy about the darn freaking monsoons. Okay, because the nights are cloudy almost every night out there now because of this. And I'm gonna just yes, another week. I want it to be now. I'm gonna just quickly look here. If I do this, let me check out the cloud situation. Oh, geez. I guess it won't be happening tonight either.
There's rain up north. There's rain.
Yeah. There's a pretty good thunderstorm out in Wilcox, Arizona. We're in Benson, and that just is not going to be conducive to anything. It's been coming from northeast to going to the southwest. So this big storm is heading right for us in Benson.
So I guess you won't be streaming for a few days.
No, so I'll show you if I can just get this to show you real quick.
Look at this. Wow, that's a lot of clouds.
Yeah. And you can see that there is
lightning strikes. Yeah.
There's Benson right there. Okay, and there is the storm that's coming down. You'll notice it's actually going toward Benson.
Yeah.
Go away. It just isn't going away.
No, it's big. That's great, though. It'd be nice.
Yeah. See, I kind of broke that radio wall kind of a thing where you turn the camera around and show people what's going on.
Oh my gosh, Mark.
I don't have a problem.
So risky.
I like it. It's okay. Yeah. So bottom line is that we're going to have to just play it by ear. That's the only reason. That's why I wrote the post yesterday on Facebook and other places to illustrate why we're not streaming. It's not like we're going away. You have no idea how much I can't wait to show you guys this summer Milky Way.
Oh.
And on rare nights where it's been kind of partly cloudy with storms coming, you see the lightning in the distance heading toward the observatory, but it's clear that moment at the observatory, I can't risk opening the building. Because if something happens like has happened in the past, I don't want the building stuck open. And then
lose power and the roof is off.
Yeah, exactly. And the roof is off. That's happened too. It's like, oh. And now we have 2 telescopes in there, so we have twice the risk. However, there's been moments where it's been clear, and I use my security camera, which is an ordinary WYZE security camera, pen and tilt. I point it up in the sky. you can see the Milky Way. And then you see the flash of lightning below it. It's like, nah, not tonight, pal, not tonight. Right? So
Yeah,
that's
it's
pretty
gorgeous.
bad. I just don't like that. But that's what happens, you know?
Well,
That's
you
what
need to get your Connecticut scope up and running so that when it's raining here, you can be streaming
Well,
from.
well, that's going to be a solar scope. So
Oh, it
that's
has to be
not.
during the day, right?
Yeah, I'm going to do solar here. That telescope. Not sure what I'm going to do with that telescope.
Huh.
I may choose to. You know what? I may choose to auction it off to a Sky Tour listener.
Ooh,
Hmm,
wouldn't that be cool?
I might just
It's
do
a nice
that.
telescope. It's
It is. It's a
beautiful.
10-inch. It's a 10-inch f6.3 system. It's a little
Mhm.
faster. Yeah, really nice. It wouldn't come with that. Well, you can't tell, but it has a refractor mounted on it right now. And it is on a fork mount as well, but it can be deforked. Anyone can take off the forks. Yeah, I mean, I was surprised how easy it was for this telescope to be taken off the forks and put on a German equatorial mount, which is the mounts that like this right here. This guy here, that's a German
Mhm.
equatorial mount right there. Okay,
Okay,
you don't see the two forks on either side of the telescope. Okay,
right.
that's typically how Schmidt Cassegrains comes with the fork mount. But those are limiting. You know, you with a German equatorial, that thing swings up into position, so you could literally swing above the roof and look around, okay, at everything. And then when you park it, it goes right down below the roof. That's what we've done right now
Really
with our
great.
system. Oh yeah, you
It's
know.
what an improvement, you know.
Oh, it is. It is.
Mhm.
You know, and so I think I've shown folks what was happening, what we're doing. But I'm gonna see if this will help us. Let me
Yeah.
try just 1 second here. I want to show you something. And I'll do this. You can't tell what I'm doing. I'm going to tell you in a sec.
Well, it's good that you're telling us what you're doing. So,
Yeah. Yeah, I'm trying to bring up the observatory like it is right now. Okay, so I've got this one and this one. Okay, and let's see if
why?
that works. Now I'm going to do a present arms, and I'm
And
going
here it comes.
to share a screen. And it may just do a screen rather than a window. I gotta see.
Let's
How do
see.
I show a window? I guess I didn't even think about doing that. Let me try again. Let me see. I should be able to present. Share screen, image file. Okay.
Okay, we already got an opening bid on your telescope, Mark.
50 cent Dan.
Opening.
Final offer. Dan, that's funny. I know you wish it wasn't, but it
Yeah.
is. Yeah.
So, and Corin Lewis has clouds and Sasha dust here in Barbados. Wow.
Barbados. Yeah. Wow. Hey,
Barbados,
Corin.
duh.
I
Wow,
I went diving in Barbados one
beautiful.
time.
Oh my
In
goodness.
fact, it was in Barbados where I panicked the entire shoreline lifeguards because I had been working on breathing techniques to allow me to hold my breath for a lot longer. I got up to 9 minutes.
Oh
9 minutes.
my God.
The record is about 20 minutes, by the way, not
9
by
minutes
me.
is a long time.
Imagine being able to hold your breath for that amount. I could never
No,
get close to that, but I
I
got to
could barely get
9.
a minute.
So what
Wow.
I did was I started working in my pool that I used to have, and I would just go underneath and just sit still. And the first time, 30 seconds, next time, 35, then 30. And it was going like this, but it was going up. So eventually I got to 3 minutes. Wow, that's a long time. I felt like that's really cool. So then I just kept doing it and doing it and doing it all summer long. And I got to 9 minutes. 9 minutes. And I couldn't believe it was 9 minutes, but it was. And so then I went to Barbados and I was snorkeling. And I said, hey, let me try dive down. I looked underneath and there was a dive team on the bottom, a scuba class. I felt their bubbles on my body. I was like, whoa, that's weird. And it was bubbles from
Ah.
the scuba team. Yeah. You know, expelling carbon dioxide on me. So I dove down after taking my breaths that I normally took to go diving. I propelled down 30 feet because that's where they were. They were 30 feet
Ooh,
down.
that's deep. Mm-hmm.
And I stuck my flippers underneath a rock and I just sat there and watched them. And they're in a circle about 20 feet away from me, and the water's beautifully clear. And I'm just enjoying this nice silence. You can hear the bubbles, you can hear sounds under the water and stuff of not people, but fish and so forth clicking and stuff.
New universe.
And then the dive master of the team looks over at me, and then he turns back to the group. Then he looks over at me again. He goes to his regulator. He says, "Do you need air?" I went, "No, I'm fine." He's like, and then he comes over. He swims over. He says, tells his team to hold on. He comes over. He goes, "What?" I go, "Fine. I'm here. I'm fine. I'm good."
As your
You want air?
purple.
No, I wasn't though, because by this point I was 6 minutes in out of the 9 minutes that I could do. But because I expended effort to dive down there, I was getting close to needing to go up, And so when 7.5 minutes or so rolled by, I realized I should head up, and I went like this. I went like that to the guys. They're like, and then I went back to the surface, and then. I didn't do it again. And then when they came out of the water, the guy comes up to me because when he came to the surface, he was like, "What the hell are you doing?" I said, I've been doing, look, I'm not trying to be a deep diving guy, but I was just trying to learn to hold my breath. And I got up to about 9 minutes, but I could only do about 7.5. He goes, 9 minutes, 7.5. I can't even do one. I said, "Well, you know what? It might help you if you're doing diving and say you run out of air and you don't calculate it correctly. If you're not doing a decompression dive and you can just bolt to the surface, it might help you to be able to hold your breath for a little longer." And he's like, "Well, that was kind of irresponsible of you to do that in front of my dive team." I go, "Oh, I was not at all trying to insult anybody, and I certainly wasn't making fun of anybody. So I'm really sorry, man. I didn't mean that." So as it turned out, yeah, he wasn't really mad at me, but I just thought it was
it
pretty.
personally.
Well, it was pretty funny.
All you got to remember, though, is when you're coming up and you think you're out of breath, just don't panic and just go slow and calm, and you'll make it to the surface. So
yes, you will.
Because people start panicking and doing this, and then it slows them down. So
yeah, and they end up using more air. That's right. And that panic thing is something that I was subject to myself a couple times. So
scary.
I get it. All right, let me do this now. I'm going to try and do this now. I'm just going to kind of share what's going on here.
Please do.
I'm going to share a screen. Oh, look, I can do a window. How dumb. I'm an idiot. Sorry.
Mark can learn.
Yeah, I can do it.
Send your dollars now.
Yeah, right. So here is the current view.
Yes, Mark, here's a real quick. You can go diving for pearls.
Yeah. Thank you. That's Courtney. I know her. Cornucopia. Thank you. I'm going to go diving for pearls, but they're probably going to be coming out of me.
Oh, that's funny.
All right, so this is the view. Neat. This is the view inside the building in Benson down below, and that's the view up above, right? And it is a pan tilt camera. So what I can do in here, we have the sunlight in the view, so I'm going to move that around, see if we can get rid of that. All right, so let's move that. No, don't update my firmware. So we're going to move up, and you can see the clouds we have there. Right, it's kind of bad. That's the roof that opens in our building. I wish I could show that to you now, but I can't. But it's a really nice ground. So what I'll do is let me make this bigger.
There you go.
Yeah, make it a little
that helps. There. Okay. There you go.
Yeah. I was looking at the camera one day and I saw a bird just like flying right at the camera, and it landed on top of the camera.
Oh, that's hilarious. Hope he didn't leave any trace.
No, he didn't.
Okay, good.
But if you look in the hill here, let's go up to look in the hill.
Yeah.
Right. Up here, this is another observatory up there. And you can see the dome up there. And there's a geosynchronous satellite station up there where they're looking at 30 geosynchronous satellites at night when it's clear. And there's a 30 by 30 building roof that rolls off up there, and there's
Big.
telescopes just sitting on permanently mounted, positions, so they're not moving because geosynchronous satellites sit over the same place on Earth at all times, so they're always in the telescope view. Okay,
Oh, that makes sense.
yeah, and you can only see them at night, of course, and not on a night like this, unfortunately.
Mhm.
So yeah, so this
Cool.
is really pretty. And then if we look to the right side, okay, you can see that the gray clouds are still there as well. And then once we get out of there, you can see that the view is a little better looking because you don't
Yeah.
have that glare from the sun.
Well, you're
You
starting
can
to get a
also see,
sunset.
yeah,
It's
you're
gonna be
right.
pretty in a few minutes or a
That's
little bit.
it will.
Mhm.
And you can see there's the door to our building right there. But
Yeah.
this gives us a really good view of the grounds. This camera is set to automatically track motion. So many times we'll get an alert. It'll be a car right there in the driveway. And that's because there's a guy that comes out to service his telescope who lives nearby. All right, so he'll come out there at that time. But that's that is this view, and then this view here. This is the 11-inch telescope to the right there, and then that's the that telescope is a full uh, high focal length system, so we can do studies and look at objects up close and personal. Whereas this other one over here,
Sweet.
right there on the left, that's the
Okay.
wide field system. All right, so that one you see on the front, in the front there, it has sort of like a cylindrical thing. That's the camera. It's on the front of the telescope. All right, that's called a hyperstar, made by Starizona in Tucson. Wonderful people, great people.
It's red.
It's a red camera. That's correct. You're right. Yeah. In fact, if I turned off the lights, let me see what'll happen if I turn off the infrared lights. Let's see if it will go down to showing in color. And it doesn't. Okay, so it won't go to color yet because it's not quite enough light in there. So we'll leave it on. Anyway, yeah. So in the middle there, you can see my cursor now. There, that is the camera. Okay, and then this thing behind it is the hyperstar. It takes a telescope that was f8, a focal length of f8, which is slow photographically. Okay, kind of like this telescope here. Okay, and it turns it into an f1.8 telescope. So it literally makes it many, many times faster. Okay, and that's what this is doing.
When you're saying
You know,
faster, that means shorter processing times, right? Or
shorter processing times. That's right. Yeah, and if we look down here, you can see that that's a fan. Okay, because when I was working out there last time, it's very, very hot in there. The this is the telescope computer for this system. Okay, this system here has a computer right there. Okay,
perfect.
and that's for this system. So there's two telescope systems. However, I can make them into one. I can actually do all of this with just one system. I haven't done it yet, and it will take me a little longer to, troubleshoot that and make sure it's not going to give me any problems.
You'd have to program that.
Yeah, I'd have to program that in my telescope management program that I do. And I haven't done that yet. It was just much easier to use two computers.
Yeah.
And I'll be getting a third for the other building. Right. So that tripod is technically going to end up going away to another pier. This was a temporary way to install this from the Sonoran Desert because the pier from the Sonoran is shorter because the building height was a lot lower. Okay. You remember
Yes, it
walking in
was.
there, you can hit your head in the ceiling
Mhm.
because it was so low. This one here, this is a 7-foot ceiling. So the telescope has to be a lot higher to see you better. All right. Yeah. So
See
that's,
the universe with.
yeah, I know. The better to see you with, my dear.
Mhm.
Yeah. So anyway, that's that, and that's kind of cool. Now, I did want to take us down another path here,
Okay.
and this is interesting because one of the things that we not expected to see is finding a gas cloud, okay, called Cloud 9 of all things. Right?
Oh,
Yeah.
Cloud
And
9.
yeah,
Uh-huh.
and Cloud 9 is a fascinating cloud, which we can't really show you other than by looking at sort of a, a radio or infrared system. Maybe James Webb looked at it,
Hmm.
um, because it's a cloud of pristine gas that kind of looks like a galaxy, but with not one single star. It's a
Ah,
cloud that has no stars. It should have stars in it. If it's a kind of like a galaxy,
yes.
it
That's
should have
weird.
stars, and it doesn't have any stars. So that's a rare
So
occurrence.
it's just like elements then that haven't
It's
collapsed.
gas. It's like
Yeah, it has.
gas and dust like galaxies have, but with not a single star from any of
So
it,
this,
which
hmm.
doesn't make much sense.
Are there
You know,
planets but no stars?
um, not that we can tell. I mean, it's just a gas cloud. But I say that kind of hesitatingly because we can have rogue planets that form without stars, and that's something that we can have,
Hmm.
right? Now, uh, this particular this particular Cloud 9 seems to be a relic from the early phases of galaxy formation that somehow forgot to make stars. And so it's an interesting dilemma that we don't understand, you know?
Could it have cooled faster or
Uh,
something? And maybe, I don't know.
who knows? We don't
Mhm.
know. We have no idea.
Huh. So do you have
Another
a picture of it?
huh?
Do
No,
you
there's actually there's no image of it. It's just
black?
a cloud. I don't have Cloud 9 image. I'm sure it's going to be a similar image to this guy. We're on the right where you're
Mhm.
going to see this kind of structure,
Cool.
like
Okay.
maybe one of the ones at the top there, the top right bright one in the green. Okay, something similar to that looking. Um, so I'm not sure now. Another weird thing is that we look at our solar system and we have the Jovian worlds, right? Jupiter, Saturn, Uranus, and Neptune, right? And they're very much cold. Gas giants, most gas giants out there, except for a very few, like what are called hot Jupiters, are either freezing cold or scorching. Okay. So Jupiter and Saturn are freezing cold, obviously, and Uranus and Neptune are as well. And the hot Jupiters are the ones that are just big, giant, puffed up balls of gas close to their star. And those are the scorching hot Jupiters. Well, uh, TESS object of interest, TOI 199b, little b for the planet name. Okay. TOI 199 is a star, and TOI 199b, okay, that is actually this little tiny planet. It's actually a major size gas giant. It happens to be a, a temperate gas giant, meaning it's in a habitable zone where the temperature is about 175 degrees Fahrenheit and the atmosphere is heavily blanketed in methane. Now, at
Oh.
some point under that methane blanket, we might have a potential for some kind of airborne life. Interestingly, it
Hmm.
it isn't going to work on a typical oxygenation type process. It's not going to probably going to be chemosynthetic, not photosynthetic, right? But it's still pretty interesting. So that is a weird thing that's going on out there. TOI 199b, another news note
Huh.
of interest here. Now, another thing that we found recently on the Perseverance rover at Mars is this. Now, you might say, what is that?
Oh,
Well,
what
that's
is
rock.
that?
I'm glad you asked. Okay. Okay. That is right there. That is, you can see that the Martian surface is there. Okay. But you're also looking at, if you notice, these dark black, what look like freckles
Little
on the
globs.
rocks. You see those?
Yes. Uh-huh.
Yeah.
Yeah.
Now, what's interesting about those freckles, in fact, is that they're not freckles at all, potentially. In fact, they might be it might be what's keeping scientists up at night. These rock samples from Mars, these images, show this peculiar chemically altered leopard spots on the surface of Mars. Now on Earth, get this, these exact types of chemical reactions in ancient rocks are the signature of microbial life,
Ooh.
using organic compounds for energy. It hasn't been confirmed yet, but it looks like the smoking gun is getting clearer on Mars.
They're little balls of algae.
Well, I don't even know if it's algae, but it's
I'm-
definitely microbial in nature, and maybe it's a signal
amazing.
to a time when waterborne life was common on
Yeah.
Mars at some point. Right now, though, this is what we got, and so
That's
those things seen by the Perseverance, and no, those are not dog turds. Okay, I know someone said those are
Kind of
dog
looks like
turds.
slugs or something. Yeah.
Yeah, no, and it's not fish poop or whatever.
Martian
Okay.
dogs. Yeah.
Yeah, it is an interesting shape though. But those leopard spots are the most fascinating remnants of what could have been ancient microbial life on Mars, and could be something that will last for a lot longer in the scientific annals as a harbinger of signature of early life on Mars. Really cool.
Is that found in like a lake bed or something, or is it all over?
Yeah, no, it's in it's a particular location seen by the Perseverance rover. I think it was in Jezero crater, which was a lake at one point, filled lake. After the bombardment area where the craters were created.
Yeah.
So really interesting. Now, I early on, and this will be the last thing I think we're going to talk about, unless you have other things to mention.
No, we got 5 minutes, so we're doing great.
Good. Yeah. The Hubble and the Webb have been tasked with finding what's called a missing link black hole. I mentioned this at the top of the program. Black holes, the concept here is this. Okay, we see tiny stellar mass black holes. Okay, we see supermassive black holes like in the center of galaxies. The Virgo galaxy at the center has that beautiful orange, rendered black hole that we saw taken by the Event Horizon Telescope, which was a bunch of telescopes around the Earth that were looking at the Virgo galaxy 44 million light years away.
Wow.
And it was using a telescope, making a telescope. The Event Horizon Telescope was effectively the diameter of the Earth, which is 8,000 miles. So telescopes dotting the Earth would look at this as the Earth rotated. They would look at it, and then they would take that data strip and basically turn it into an image of what could be considered high resolution for looking at a galaxy so far away, and they could visualize the black hole in the middle of this galaxy.
Oh, cool.
Why could we see it? We see it because it was the largest black hole that we've ever seen. It was the size of like 6 solar system diameters. That's how big.
Wow.
In fact, its existence may have sparked the thought process that the entire universe is a much more cataclysmically massive black hole that we're inside of, for all we know. Okay, kind of cool.
It is cool to think about.
Yeah, it is. Now, the thing is, though, so we see those supermassive black holes. We see stellar-sized black holes and what they do. We saw the supermassive black hole at the center of our galaxy, right? Those images saw that image of the stars rotating around and go zing, zing, getting whipped around by this black hole. Okay, well, what's missing though is the missing link, and that is the stellar-sized black holes versus supermassive black holes. But what about stuff in between? What we call intermediate-sized black holes. Not found. Where are they? Well, let's go to Omega Centauri.
Why wouldn't there be any? That's weird.
Well, there is. There has to be, right? We always know there is. So here, this image, shows us in this image here, they finally confirmed this long sought after intermediate sized black hole hidden inside the massive cluster known as Omega Centauri.
Wow.
The biggest apparent diameter, globular cluster that we can see. In fact, our Benson telescope can see it just barely.
It looks like grains of sand.
I know, but they're all stars in this particular
Wow.
location. And in the inset there, you see an inset, and there's a red square inside the middle there. But then in the inset of that red square, you can see the circle. That red circle is circling a star, okay? And that star is a companion to the intermediate sized black hole they've been seeking. By studying that location and that star, they've been able to figure out that this particular black hole is indeed the missing link.
Wow.
Just like with human evolution, okay, we've now found the black hole missing link, and that's exactly what that is right there.
Wow. And what are the chances of finding that in that picture? All those little stars. That's amazing.
But if we're
Cool,
gonna do,
cool.
if we're gonna do a study, we would be able to find it, and
Yeah.
maybe what we'll do at some
Wow.
future point is talk about that study and see, how we might be able to contribute to that.
Yeah. That's
Right.
neat. That's
So we've
neat.
had
Oh,
a good time tonight. Yeah.
oh,
So
so
again,
much interesting stuff.
yeah, 2 hours of absolutely,
Yeah.
what I say was 2 hours of the bleeding edge of the universe here. Okay.
Wow.
Yeah.
Glad
That's
there was
pretty
no
cool.
blood. Yeah.
I know. Well, you're on the leading edge or the bleeding edge, right? And so talking about it was very cool. And I think that was really enjoyable. I hope that people enjoyed that. I want to thank you for your question. And I see a bunch of people here that I know. Good vibes. Hi, how are you? I know you. Nice to see you. And Kevin says, great show. Thank you both. Oh, you're more than welcome. I thought that was very nice of you to say. And I, Charles Smart, that's good vibes. Charles Smart says, adrenaline loves to suck up your oxygen. Yeah. And we were talking about going down in the ocean, holding your breath.
Yeah.
Yeah, that's true.
That's good.
I tried to stay calm during that, Charles, so that I can actually get it back,
Yeah.
and it was cool. And I want to thank Colin from Barbados for joining us tonight. Thanks for coming by.
Yeah.
And
Thank
to all of you, and you especially, Tara,
Thank you,
thank you for
Mark.
putting up with me. Well, thank you for putting up with me.
Oh,
And
thank you.
it's been a while since we've done a live show. I enjoyed it, and hopefully you guys liked it. Let me know in comments or what have you that if you liked it or not. If you didn't like it, tell me anyway. It's okay.
Tell him.
Anyway, yeah. Tell me. Don't tell her. She'll just say it was kind of good.
Oh,
But thank you guys for joining us tonight. If you have anything you'd like to see on Sky Tour Radio, let me know, because we'll
okay.
be happy to show you and go through it again. So you have a good night, and we'll talk to you
Thanks,
on the
everyone.
other side. Bye-bye.